Great. Okay. Now, we've been talking about, we've started to introduce eccentric connections, right? Eccentric connections. What's an eccentric connection? What does that mean?
Loading isn't necessarily through the center of stiffness.
Loading isn't necessarily to the center of stiffness. Yeah, I don't see any red lights coming on there. I will ask that question. Usually they do, I think, when you push the button. So I will ask. Everyone push their button. No? No red lights on it?
This one works.
That one's got red lights. The front two rows do not have red lights. Guess what? They get to answer all the questions in the back. Okay, just so you. So we've been talking about eccentric connections. This connection, is it eccentric or concentric? Eccentric, because the load is not going through the center of stiffness, right? The load's not going through the center of stiffness. And so I ask, what is the classic solution to this problem? What's like, from what you know so far, what is the classic way to attack this problem? Well, you break it up, right? You break the load up into some kind of shear component and into some kind of torsional component. Right? Yeah? And hey, we did that. Boom! It appears magically. We did that. We had the shear component, right? We had the torsional component. We added these two components together, right? Got a resultant from each one of those, and it looks something like that. So this is what the stresses look like, right? Yeah? Okay. Well, this is our center of stiffness, and one thing that I didn't draw last time that I probably should have is that if we go perpendicular to each one of these vectors and draw a line, so say that's a line, do the same thing here, that's a line, do the same thing here, that's a line, here, and here, at one point, it should all correspond if I drew them perfectly. Hard to see what I'm doing, huh? So I basically drew a vector that's perpendicular to this, or a line that's perpendicular to this. And there's 100 of them, right? There's a whole bunch of them, right? Same thing. Drew a line through this, a line through this, a line through this. But in only one spot do all these lines coincide. There's only one spot where all of these lines meet. Okay? All right? And that's called the center of twist. And what that really means is if we're changing the problem into an equivalent torsional problem or bending type problem, this would be the point where the connection would be trying to spin around or twist around. Okay? But I want to add some in this. I want to add the word elastic. The elastic center of twist. Okay, because you probably don't realize this or think about this, but we're assuming if this is our limit state, then as soon as one of these bolts reaches their limit state, we have to stop, right? 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 We have to stop because we don't really know what to do. But we know that's not right. We know that structural resiliency tells us that even though one bolt reaches its limit, we can keep going, right? Keep going. Keep going till what? Either all the bolts are at their limits, or until one bolt gets so overloaded that it fractures, right? It breaks on its own. Okay. Great. We know that's what's going to happen. And we're going to find out when that happens that a lot of these assumptions that went into this problem are wrong. And things will change. And if you've maybe seen this in the past where you talk about the neutral axis, the elastic neutral axis, or the centroid of the member, and then you have something called the plastic neutral axis, right? That's the point where things bend about right as they plastify. And they're not always the same place, right? And we're going to find out in this problem that just because we have an elastic center of twist, that we're also going to find something like an inelastic center of twist. Okay? They're going to move. So that's coming up. Any questions on that? Okay. More is coming. More is coming. So don't worry if it's not 100% clear yet. So, like I was saying, that these type of force diagrams on our bolts and these type of force diagrams on our welds, all elastic assumptions, all of these assumptions that we used from strength of materials, really the same type of techniques, are the classic way to work the problem. Okay? About 8 years or so ago, they started to realize, hey, this is a lot of work, and this doesn't match test results at all, because they weren't thinking about, structural resiliency when they came up with this concept for the first time. They were just thinking, yield is scary. Let's stay away from yield. We don't really know how to handle the problem, so we're going to make some conservative assumptions, and that's fine and conservative. But if we can work something, if we come up with a technique that is also conservative, maybe a little less conservative, but still safe, that's always good. So again, this original assumption assumes there's no yielding in the plates, the bolts, or the welds. There's no slippage. Forces from the moment on each bolt or weld is proportional to the distance from the center of stiffness. That's kind of all the stuff we talked about before. We had this is the elastic analysis. These are the mathematical equations we used to use to figure out, basically come up with the capacity of each one of the magnitude of each one of these force vectors, and they're always perpendicular to your center of stiffness. This is where this stuff started. Oh, there were some very unfun problems in the past. Okay, that ones that took like 6 pages to work. Okay, not very fun, and it kind of made your heart hurt a little bit at the end of it when they'd say, you're about 50% conservative. It's like, I just spent 6 pages of calculations, and I'm off by 50%. Yeah, that's what it came down to. But yay, progress. We learned. We've come up with new techniques. So again, the assumptions of the previous elastic is that everything must remain elastic. These assumptions are far from what actually happens, but lead to very conservative results. These techniques can still be used in connection design, but it lead, again, to extremely conservative results. Tons and tons of math. No fun for anybody. The elastic analysis, again, assumes that all bolts and welds remain elastic. If we allow some inelasticity in our connection, yielding or slippage, we will find that our capacity will increase. What are we talking about? Well, those pictures I drew. Again, if we come up with this idea and concept that when we drew this, that if this is the limit state, if this is it, there is no more. We have this bolt that we're not even really loading. Then why is it there? Let's just take it out, right? Well, one could, right? One actually could, if you're using this elastic analysis, and you'd get no difference in calculated capacity. But that doesn't make sense. How can you take a bolt out and have it not add to capacity, right? That doesn't make any sense at all. Okay? And what we're going to find is that eventually, that every one of these bolts are going to reach their limit state, right? Every one of them. And that's going to require some localized yielding and localized movement of our plates and our bolts. And we've got some safety factors built into our techniques so that no individual bolt will fracture. And what we'll find out is a really easy, simple solution that provides conservative results. And who doesn't like that? Right? Who doesn't like that? Okay. Let's see. We'll find our capacity will increase when a bolt or segment of weld yields. The connection does not fail. Instead, the load is distributed to the other areas of the connection. The connection will not fail until all of the resisting elements are at yield, or if strain capacity is exceeded, and there are safety factors in the equations that do not allow strains of individual bolts to be exceeded. Well, The ones in the manual don't allow it. If you had some, let's say, and architects never do things like this, ever. Let's say they wanted a star-shaped bolted connection. Now, I'm not sure why they would ever do that, but let's just say they did. Some kind of crazy star-shaped connection like this, and they're loading it, and you can't see it. Yeah, now you can appreciate the absurdity, right, of some connection like that, right? There's no guidance in the manual on how to handle this. And what they actually tell you is to use a rational method. Use a rational method. So to be rational is to convince the architects that this is a really bad idea, right? Yeah? Okay? Now, if you absolutely had to do something like that, maybe we can think about something like that for a homework problem. I don't know. We'll see. We'll think about that. That's all probably even too evil to put on a homework assignment. But what one would do is this idea that the individual strain capacity is not exceeded now becomes very important for this bolt and this bolt. Okay? If we assume this, all of these are going to be yielding and all of these are going to be at their limit state, this bolt and this bolt may no longer, that may be a very bad assumption. One would have to test that. And you'd say, well, how do I know what kind of strain capacities I'm going to be able to get out of these bolts? Oh, good luck. You need to do some tests. Okay? You need to ask the manufacturer what kind of strain capacities they think they can get out. Then you may be able to draw it up in AutoCAD, do some kind of rotational analysis, right? And see how much rotation you think you're going to need. And then you may need to back calculate and see what strains that'll be placing and see if you're within the allowable limits. Or you can just do the elastic analysis, the old school one. Remember? One we just did on qualitatively here? Yeah? Yes? Okay, whatever. Yes. Therefore, twisting about the elastic center. That's that center of twist. This elastic center of twist. Okay? Therefore, twisting about the elastic center does not actually happen. It is a lie. And the reason why is because in this analysis, and we'll show this together when we do this big full-scale bolt test, in this analysis, we assume that each one of these bolts are loaded equally. What if, like on your homework assignment, we have a bolt that's not engaged? It's not being touched. There's no load transfer. Air is not very strong. Okay? If we're relying on elastic-based techniques, that breaks everything. Because this can't happen anymore. So our center of twist may not actually be here. Let's say this bolt, the one we're relying on so much to be engaged, isn't. Well, then if that vector goes away, that's going to change where the center of twist is. You with me? So it doesn't actually ever happen that way. But it's a great make-believe story. Okay? Makes you feel good inside. Right? Therefore, twisting about the elastic center does not actually happen. Instead, a connection will keep adjusting until all of the bolts or welds are at capacity. The instant before failure, the connection will twist about a point called the instantaneous center. Ooh. The instantaneous center. So now I've shown some connections down here at the bottom. This is some kind of bolted type connection with the eccentric load. I've showed where the elastic center of twist would be, and I'll show out here that the instantaneous center is further away from it. Does that make sense, that it would be further away? I think it should. Okay? Same thing here for this weld. Believe it or not, your elastic center of twist is going to look something like that. Okay? Be somewhere like that, and that your instantaneous center is actually going to be even further outside. Now, depending on how long your legs are, your elastic center of twist may be here. Okay? It may move around in here. The point of the story is that they will move in this direction. This is going to move in this direction. They're going to move. These are for symmetric connections. For unsymmetric connections, they can move in odd ways. Okay? They can move in odd ways. You with me? Now, if you ever run into some kind of crazy connection, you can, and you want to justify why you want to go with something that's a more standardized connection, very easily you can calculate the capacity using this elastic analysis and this inelastic analysis, and you can show there's about a 30 to 40% difference in connection material needed. So imagine saving 40% on every single connection in your structure. That is a lot of money. That is a whole lot of money. Okay? And architects, even though they love beautiful things, I do too, usually when you start talking real money, they'll start agreeing with you. Unless their name is Santiago Calatrava, but that's a different story for a different day. Okay, so let's do some full-scale bolt testing. Great thing about Calatrava is that every single bridge that he has ever designed, every single one, has cost 10 times the engineer's estimate. He owns that world record. And as far as I'm concerned, he can keep it. Okay? Okay, so I need 6 bolts. Come over here and stand in the holes. So, come on, start moving. 1, 2, 3, 4. Are you going to fit in there, Dan?
I don't know.
Maybe? Okay. So, I need 4 from that row and 2 from the row behind it. Come in there. I'm going to make sure the hole, you're going to stand in your holes. I'm going to make sure the camera is zoomed in on you. Yeah, that's right. We need one more. Thank you, Fevin. Okay, why don't you go ahead and pick up that and hold it around your waist. Okay, so let's position the awesomeness. Okay, now, the rest of the people in the class, I want you to stand up and get close, but don't block the camera. Okay, let's see. Right here, oh, you're blocking the camera. Okay, now we can see. Now we've got all of our bolts, okay? And this is on the space up here, so you're going to have to take a half step back. Thank you so much. Great. So, if we were going to load this connection, we got bolts, right? You guys are all bolts. Yes. Okay, and I'm going to be the load. Yes. And I'm going to be pulling on this side. Now, the center of stiffness would be here. So if I pull concentrically, why aren't you letting me pull you? Thank you. Okay. Plates are moving. Who? Raise your hand if you feel it on your back. A couple of you have it. Not yet. No, you can't. No, don't lie to me. Don't lie to me. Don't tell me what you want me to hear, okay? Tell me the truth. Who can feel it on their back? Raise your hand. Not yet. Not you, right? No, you're going to have to give, because if you break this, I kill you, okay? Give a little bit, bolts. Give a little bit. Tell me when you feel it, Bevan. You feel it now. Okay, we yielded a little bit. You gave a little bit, right? Right? And that's what happens. That's structural resiliency, right? Where we start out and, this is all over the place, and Jennifer wants you to move all the way to the back for me. Okay? Great. And I start pulling on it, and you can feel it, right? You can feel it? How about you? No. You're going to give a little bit. You're going to give a little bit. You're going to give a little bit. Who can feel it now? Everybody. Right? Because you gave a little bit, right? And that's resiliency, right? One of them is going to give a little bit. The other system's going to keep going until the other ones are engaged. Now, let's talk about what happens with eccentric loads. First, I want you to randomly put yourself in the holes. Do a little dance a little bit, and see where you wind up. Great. Now, I'm going to start pulling here, okay? As I start pulling here, I want you to kind of like raise your hand when you feel it. All right? All right? I'm going to start pulling. You sure you feel it? Okay, good. Raise your hand when you feel it. Okay, so we got 1, 2, 3 feeling it. We got the other 3 not feeling it. Why? That's where you started in the holes, right? Right? And can you see it twisting? Yeah? Yeah. Just tell me what you want me to hear, aren't you? Yeah. It's twisted a little bit, isn't it? It's twisted a little bit. Okay? Raise your hand if you feel it. We got another one. Oh my gosh, this is like exactly, you're not feeling it yet, are you? And this is exactly what we talked about. Remember, we have the bolt here that didn't feel anything. You're feeling it a lot, aren't you? You're feeling it a lot, aren't you? A lot. Quite a bit. Right? Quite a bit. And you got nothing, right? You got nothing. Okay? And that's elastic, right? But now let's all stay where you are, and let's keep giving. You're going to have to give a lot, okay? Keep giving. Keep giving. Okay, raise your hand when you feel it. Keep giving. Keep giving. Oh my gosh. Do you feel it now? Okay. Look how much rotation we had to have happen. It was a bunch, wasn't it? Our instantaneous center has moved. It used to be like right next to Jennifer's hand over there, and now it's like through the wall, right? We're like twisting about the wall. Why? Because we had to give and give and give and give until we engaged everybody. We're just engaged right now, right? We got to get yielded, right? We got to get to failure. Well, let's just keep going. Come on, come on, come on. Okay, yeah, you fell over. Yes! Broke something. So that took a lot of rotation, didn't it? It took a lot of give, right? Does that make sense? Okay, so the point is that this elastic technique is great and easy and simple. And sometimes you use it because it's easy and it's simple. But doesn't mean it's the best way to do a problem every time, right? Any questions as we're all here? Okay, cyberspace, if you have questions, you send me an email, okay? But we've seen everything, we've seen it happen, we saw it, we get a few people get engaged, we kept going, we kept going, we kept going, we got everybody engaged, we even kept going further until we had somebody fall over, right? That's when you know you're doing something, right? Yes? Okay. Thank you so much. Give a round of applause to beautiful. Clap! Thank you. Okay, so we just witnessed with our own eyes that when we started loading, we had members and bolts that were way away from our center, our elastic center of twist, that were heavily loaded, the bolts in the corner. And Jennifer, she wasn't feeling anything right here, nothing. Okay? They kept going, kept going, kept going. They adjusted, until all of them were at their limit states. Okay? And it ended up looking something like this. And I'll ask you, what is the magnitude of each one of these vectors? The same. The same. Right? And we even know even more than that. We know that they're either going to be equal to the capacity of the bolt or the bearing and tearing capacity of the bolt. Because that's going to control, right? The bolt's either going to break or it's going to tear out the side. Or it's going to bear so much, it's going to cause too much deformation. Does that make sense? We'll talk more about that coming up, but what you usually do is you'd say, okay, well, which bearing, okay, I see all these bolts going this direction. This bolt wants to go over here. This bolt wants to go over here. This bolt wants to go here. This one here. This one here. This one here. Which distance do I use for L sub C? Remember L sub C? You have to use L sub C to calculate if it's bearing or tearing. Which one do I use? Well, what's commonly used is the most conservative. Okay? The most conservative. So even though this is at this strange angle here, people will often use, if that is the lowest L sub C, they'll often use that distance. Does that make sense? Because it's conservative. They don't want to have to think about, oh, it should be at an angle, and so it should be increased by 20%. Okay, they don't care. All right? They don't care. Pick a conservative one. All right? It's another good reason to have a uniform bolt layout. Right? Uniform bolt layout. Now, again, when we do something like welds, depending on, this is again this kind of C-shaped, sometimes your elastic center will be something like this, and this is very odd and strange for people, that yes, this elastic center can move, and it will move all the way out here. And this is strange. This vector, this weld, which you would think would be stressed in this direction, is actually ends up, the force vectors actually end up rotating. And at failure are out here. Alright? Really odd and strange. I think it's much easier to think of bolts first to introduce the concept, to make sure you understand it. But you could think of these welds as individual bolts that are 1 inch or 1 unit long. Imagine just a whole bunch of bolts side by side by side together. It's another way to think of it. And what's it going to do? What's it going to do? What's it going to do? Okay? It's another way to think about welds. Now, we are going to be focusing almost wholeheartedly on inelastic methods. There are some great examples in Salmon and Johnson, and I'm sure in other textbooks about that cover elastic method design. Okay? And if you have to use it sometime, I'm sorry. Okay? But we're going to be covering inelastic. Now that everything is happening about this instantaneous center, we treat the problem much like we did the elastic one. We have internal moments, we have external moments, and we have to set them equal to one another. The only problem is we don't know where the instantaneous center is. We don't know where it's going to be. You can't just look at a problem and pick it. If we could pick a spot and we know that was the one, the math becomes really, really, really easy to do. But we don't know. We don't know. It's hard to know where it's going to be. To find this by hand, it's iterative. Really, you just start guessing and checking. You put external moments on your section. You have internal moments from a guessed instantaneous center, and you keep guessing the instantaneous center until they match. All right? So you guess an instantaneous center. You make sure that some of the forces in the x, the y, and the moments are all equal to 0. You solve for the p and see if you got the answer that you guessed. Oh, no fun. Excel can do this really quickly. Or we can use these amazing tables 7-7 out of the Steel Manual. Okay? If you have your Steel Manual, this would be the good time to take it out. And we'll be talking about them. But in these tables, you need the load orientation, the angle that the load is applied at, the number of rows of bolts, the number of bolts per row, the horizontal distance to the center of stiffness, or from the center of stiffness to the load, and the bolt spacing. So if you know all of these things, your load angle, the number of rows, the number of bolts per row, the horizontal distance from your center of stiffness to your load, and the bolt spacing, it's cake. Okay? It's cake. Now, this is really, really important. We're going to get those tables out here and work a problem. But this is really important. Pay attention. Linear interpolation is allowed for all values except for the load angle. What am I talking about? Well, let's open this up. Let's open this up. So it is table 7. It's number changed on me. Table 7.6 starts on page 730 in the newest Steel Manual. It's table 7.7 in the other ones. It's about table 7-30. And it's cool, man. This is well worth the money of the book, man. This is awesome. You have to do eccentric connections. So if you have a load, and that load is offset, because the center of stiffness would be at this bolt, right? This is for one row of bolts. This is for one row of bolts with the load at a 15-degree angle. This is for 30, 45, 60, 75, and now we go to 2 rows of bolts. Okay? 2 rows of bolts. And they go to 3, and then to 4, and then to 5, and then to 6, and I think they stop after that. Okay? So that's your angle. And why that's useful is sometimes you'll have a number of different forces in all kinds of different directions, and you find the resultant of those forces, and you use that resultant to come up with that angle, that P in that angle. All right? Okay. Now, you need to know what the angle is, and you need to know this epsilon x, this horizontal component, this horizontal distance to the center of stiffness. Oh boy. Touch the button. Touch the button again, it went away. We need to know this horizontal component to the center of stiffness. Okay? Then you need to know the number of bolts in one row. That's not very hard. You need to know the spacing between the bolts. That's S. And then you need this horizontal eccentricity. And what this does is it takes some large number of bolts with an angle that's an eccentricity, and it turns it into an equivalent number of bolts loaded concentrically. Huh, kind of cool. For example, if I have 12 bolts in a row, and my spacing between my bolts is I have a 3-inch spacing between my bolts, and my eccentricity is very small, extremely small, then it will act as if there is 11.5 bolts there. Does that make sense what I'm saying? You'd work, and then you'd take 11.5, you'd multiply by what the capacity of one bolt was, you'd compare the bearing and tearing capacity to the shear capacity of the bolt, figure out which one is lower, right? You'd multiply that by the number of bolts. Don't worry, we're going to do that in an example problem coming up. You get the capacity. You're done. Now let's say your eccentricity gets high. Let's say your eccentricity gets something like 36 inches. Now you may have 12 bolts in there. You may have them at a spacing of 3 inches. But at a 3 foot offset, 36 inches, it's as equivalent as having 2.7 bolts loaded concentrically. 2.7 bolts loaded concentrically. You with me? Okay? Now, as your spacing goes up, oftentimes your capacity goes up. Well, your moment arm gets larger, doesn't it? Your depth gets larger. So hopefully that makes sense. As your eccentricity goes up, as your eccentricity goes up, the number of equivalent bolts goes down, right? Okay. Now, you can linearly interpolate between any one of these values. The only thing you cannot interpolate between is between your angles. Let's say you have a load that's at a 7-degree angle from the horizontal. 7 degrees. You cannot take a linear interpolation between, basically solve for what the value is here, solve for what the value is here, solve for what the value is here, and interpolate in between them. Absolutely not conservative. Not allowed. So what do you do instead? Use the one that's most conservative, right? Which usually corresponds with and I think it's almost always corresponds with the lower angle. Alright? Should always be the lower angle. Now, please be careful that you realize where this angle is measured from. I love putting all kinds of wild angles on homework that is a different, and you might say, oh, it's 70 degrees. You go back here in the back to use a 70-degree table. But it's actually, 20 degrees because of the way I've defined the angle. Okay? All right? So it's always defined with the vertical, okay, with the vertical for those bolts. You kind of have to think about how they're lined up. It's always defined along the long length, okay, along the down number of bolts. Yep.
Wouldn't it be the higher angle? The higher angle.
Well, let's just say this: the angle is defined like that. You're going to take for a single row of bolts. You're going to draw a line down it. Okay, you're going to draw a line. If it's this way, the bolts are in this direction. You draw a line down it. You look at the you move that parallel to wherever your load is. You look at the angle in between those, your load, and where that parallel line is drawn. That angle is what you're going to use in this table. Okay?
But the interpolation can show based on readings the higher angle is
Let's see. I disagree. If you look at, like, for example, we look at like 8 here and here. Let's see. Oh, actually, that is more. That's weird. 9. So I guess it is. So I guess maybe the higher angle. So I think, like I said earlier, you pick the one that's the most conservative. Okay? You pick the one that's the most conservative out of the table. It's in between. You pick the one that's most conservative. Now, if it's 1 degree, I mean, I think you can assume that's pretty much 0. Okay? What happens, what do you do if we have a spacing or an eccentricity or a number of bolts in a row that are not in the table? What do you do? Well, if it's in between values in the table, you can interpolate. Let's say it's greater. Let's say I use a spacing of 10 inches between bolts instead of 6. What's that? Redesign. That's a good idea. It's a very good idea. Okay? If that's not allowed, then you better get your spreadsheets out. Okay? You better start guessing instantaneous centers, right? Looking at internal moments versus your outternal moments, and keep guessing and checking. Okay? But redesign's a better answer, probably. All right? Any questions about this before we get started and do an example problem? No? This table is awesome, man. This table is really, really awesome. Okay. Now, just to summarize real quick. In summary, we talked about 2 methods for eccentric connection analysis. And which one are we going to be using, the elastic or inelastic? Inelastic. We're going to be using this one. Well, it's just good to understand the 2. It's good to ask test questions about the difference between the 2. Elastic analysis. Connection rotation is about the elastic center. You make some assumptions that there's no yielding in the bolts, the welds, or the plates. There's no slippage between the connection plates. What does this mean? The load from the eccentricity is proportional to the distance from the center of stiffness of the connection. That's from the bending. It's extremely conservative. We talk about inelastic analysis. The connection rotates about the instantaneous center, not the elastic center. The instantaneous center. Yielding of bolts or plates or welds is totally allowed. Slippage between the connection plates is also allowed. The load in the bolt or the weld is equal to the capacity. Closely matches test data. Instantaneous center is hard to find, but those tables make it a whole lot easier. Excel makes it a whole lot easier after you get it programmed correctly. So now let's work an example problem. Okay, so we're going to take 3/4 inch A325N bolts. I think those are also called Type A bolts in the new 14th edition. 3/4 inch plate, grade 50 steel. That's our bolt layout. Pretty symmetric. Okay, so now we're going to start out with a table. We're going to find the table that has 2 rows of bolts. 2 rows of bolts. So, at least from the 14th edition, if you're dealing with the 13th edition, you should be able to use table 7-8 on page 738. On the 14th edition, it's going to be table 7-7 on page 7-36. I'm going to work it as if it's the 13th edition because that's what my examples worked out for. You can prove it to yourself if you have the 14th edition. So we need a couple things. We need epsilon x. We need this horizontal distance from the center of stiffness. And how did I know that's the center of stiffness? Well, that's kind of by inspection. Okay? It's kind of by inspection, that's the center of stiffness. But if it's not, you could actually find the center of stiffness much like you would find the centroid. You would define one of these as being your 0, 0 point. Every bolt would have a stiffness of 1, right? And you'd find what the x centroid was away from that 0, 0 point. You'd find what the y distance was for that 0, 0 point. And you'd find your center of stiffness. All right? Okay. By inspection, it's there. So you're going to need something called E sub x. And E sub x is your horizontal distance to your center of stiffness. And for this problem, it's going to be 3 inches plus 1.5, 4.5 inches. Okay? And now you need your spacing between your bolts. And what's that equal to? 3 inches. Okay? And now we need to look very carefully at our manual, and we need to actually look and see what our bolt spacing is. And we're lucky on table 7-7, and oh my gosh, they've already got something in there for a bolt spacing of 3 inches. That's cool. It's very cool. And they've got, let's see, what else do they have? They have some 3-inch ones, got some 5.5 inchers, they've got some 8 inchers. So what happens if your numbers are in between there? Interpolate. Solve it once for 8 inch. Solve it again for 5.5 inches. Interpolate between the two values. Okay? It's just fun to do. So our spacing, which I'm going to call N, our spacing between our bolts is 3 inches. Great. So we're gonna look at our table and our E sub x, and we're gonna look at our C value, and we're gonna find that our E sub x value is 4.5, and there's an E sub x value for 4 and for 5, and we're looking for 4.5. The E sub x value for 4 is 3.06. For 5, it's 2.59. And if you interpolate, you get 2.83. You should know how to interpolate by now. And you should be able to do it pretty fast. Now, this means, therefore, this connection has an equivalent strength of 2.83 concentrically loaded bolts. You say, hey, but there's 6. Yeah, but there's 6 at a pretty decent moment arm. It's equivalent to 2.83 if it's concentrically loaded. Okay, so let's say we're going to use 3/4 inch diameter, A325N bolts. Our plate is 3/4 of an inch thick, and it's grade 50 steel. And if we just look up the shear strength of a bolt, we'll find out it's 15.9 kips, at least in the 13th edition. I'm sorry, yeah, the 13th edition. And we'll find out that it's actually 17.9 kips in the 14th edition. Changes a little bit. Now we're not quite done. We're going to do a bearing and tearing calc next. I'm not going to have time to do it today in class. We'll do it first thing on Friday of next week. We're going to do a bearing and tearing calculation. Alright? So we're not done. And we're going to figure out which one is lower, and that's the one we're going to use. We're going to take our capacity, and we're going to multiply it by 2.83 volts. Does that make sense? Okay, we'll do that next time.